Hi everyone. Today we will discuss scalars as well as vectors. So let us first define this scalar and then we will define this vector. So scalars are those physical quantities which are having only magnitude. So this is having only magnitude. So it can be defined as completely specified by a number and a unit. Only it has a number. When we say number, it means it has only the magnitude part of it. And therefore have the magnitude only, and they are called scalars. Some physical quantities which are scalars are your mass, length, time, volume, speed, density, energy, temperature. All these are supposed to be scalar quantities. Now, scalar quantities requires only magnitude for its complete specification, and as far as the scalars are concerned, we have only the algebraic addition. Because scalars, they don't have any direction, so there is the operation based on scalars can be based on simply the algebraic addition. Because suppose 2 meter, 3 meter, if we need to add it, it will be 2 meter plus 3 meter, that becomes 5 meter, and so on. So that is the scalars. As far as the vectors are concerned, so vectors are quantities, physical quantities which are having magnitude as well as the direction. Magnitude as well as the direction. And quantities having magnitude and direction, in general they are termed as the vector quantity. But if we limit ourselves only to this definition, that vectors are those quantities which are having magnitude and direction, then there are certain terms which gives us some contradiction. Just like suppose pressure. So if you consider this pressure, so pressure, it is defined as P is equal to force per unit area. So magnitude of the pressure is force per unit area. Whether it is your pressure in general, or you consider the atmospheric pressure or any other pressure. So if we represent this P, pressure as P, so it is force per unit area. Now, so this is the magnitude of the pressure. As far as the direction of the pressure is concerned, the direction of the pressure is such that it always acts perpendicular to the surface in contact. Perpendicular to the surface in contact. So suppose here, if my hand is like this, the atmospheric pressure, it will be perpendicular to this surface. If I orient my hand in this position, so it will be perpendicular to this surface. If I orient it like this, it will be perpendicular to this as well as suppose this. So as the nature of the surface changes, according to the direction also adjusts itself such that it is always perpendicular to the surface. So here the direction of the pressure is perpendicular to the surface. Magnitude of the pressure is force per unit area. So there is the magnitude, there is the direction. It means according to this definition, it should be considered as a vector quantity, but it is a scalar quantity. Pressure, it is not a vector quantity, it is a scalar quantity. Similarly, if you take the electric current, so if we consider the electric current, so suppose we take a simple circuit, electromotive force of this, EMF of this cell, it is supposed to be at a resistance of the circuit, let us say R. So the current I will be flowing in this circuit. So I, it is equal to V upon this R. Now if you consider this current, electric current, so this is the magnitude of the electric current. I is equal to V upon this R. The direction of the electric current is such that it always flows from the higher potential to the lower potential inside the circuit. Inside the circuit. This is outside the circuit, so we can say higher to lower in this direction, but that is not the direction of the current. It is always higher to the lower potential inside the circuit, just like this. So it means again it has the direction, it has the magnitude, so it should be considered as a vector quantity, but electric current, it is not a vector quantity, it is a scalar quantity. It means this definition of vector, it is not sufficient, that a physical quantity is having magnitude and direction is a vector quantity. It means there must be some other condition so that we can get this I quantities like electric current, pressure well defined as far as the scalar or vectors are concerned. Now, quantities having magnitude and direction. Initially, all physical quantities were categorized under three groups: scalar, tensor, and vector. Scalar, only magnitude; vectors, tensor, magnitude as well as the direction; and vectors, magnitude, direction as well as which follows the geometrical addition or the vector addition. So quantities, physical quantities having magnitude, direction, and if it follows the triangle law of addition, if it follows the triangle law of addition in particular, or in general we can say the geometrical law of addition, then those quantities are termed as the vector quantity. Now when we add the third condition, nowadays there is no concept of tensor. Initially it was scalar, tensor, and vector. Scalar only magnitude, tensor magnitude as well as the direction, and vector magnitude, direction as well as which follows the triangle law of addition. This clear? Now there is no concept of that tensor. All physical quantities which were kept under the tensor, nowadays it is considered only scalar. Those quantities are considered scalar. So we have only two groups. One is the scalar, another is the vector. So those quantities are categorized as scalar. Quantities which are having magnitude, direction, follows the triangle addition law, they are considered as vectors. Now you can say, when we have introduced this condition, triangle addition law as far as the vector definition is concerned, then how come this electricity, electric current as well as the pressure got eliminated from the category of this vector? See this. Suppose you have this electric wire. Okay. Now the current is flowing from this direction in this wire. Current is moving from this end to this end in this wire. Now the value of the current, the magnitude of the current is I. So here the current is having the direction. Here also you have this wire like this, it stays like this, or we can have this wire in any random direction. I can put a cell here. Let us say I can put a cell here, some resistance of the wire, and the current will be flowing. So now you can see the current will be moving along the wire. However you stretch it, it will be moving or it will be flowing along the wire. Now at this point, if you consider this point, the direction of the current here, it is along the tangent to this curve here. It will be along the tangent to this curve. Here also it is along the tangent. Here also it is along the tangent. Now at different point of this curved line or this curved wire, you can say direction of this tangent here it is different from this. Here it is different from this. Here it is different from this. Similarly, when we were talking of the pressure, so the direction of the pressure is perpendicular to the surface in contact. But if the surface changes its orientation, accordingly the direction also changes its orientation such that it is always perpendicular to that surface. It means direction is there, but it is variable. Here also direction is there, but it is variable. Here it is along this tangent, here it is along this tangent, here it is along this tangent. When the direction is variable, the quantities cannot follow the triangle addition law. And just because of that, it is not able to maintain or it is not able to follow the triangle addition law, the third condition of the vector. That's why we categorize such quantities as scalar quantity of the vector. It means from this we can conclude it should have the magnitude, it should have a fixed direction. Either you say fixed direction, or if you say only the direction, it means you have to use the third condition also, that it must follow the triangle law of addition. Then only those quantities will be considered as the vector. I hope this is clear. So here, if we take some of the examples of vectors, so displacement, it is a vector quantity, velocity, it is vector, force, it is vector, moment, it is vector. Similarly, the electric intensity, it is not electric current. Electric intensity, it is again a vector quantity. Magnetic induction, it is vector quantity. Similarly, when we consider this displacement and velocity, so corresponding to displacement, we have the distance covered, and that is a scalar quantity. Velocity, corresponding to that, we have a speed, so that is again a scalar quantity. So that way we define this scalar as well as the vector. Now, how these vectors are represented? See, vectors are represented with the help of an arrow. This side it is termed as the head, and this side it is termed as the tail. This is the general representation of the vector, head as well as the tail. Here, if you consider geometrically here, suppose there is a point O, which is the point of origin. This can take some point P. It is at some distance from this point O. Is clear? So now how to represent? Let us say we consider the vector OP and is starting from O to this P. So OP. So length of this much segment, that gives you the magnitude of this vector OP. Is clear? And the direction, it has some direction. Let us say this line makes angle some theta with the x-axis. So this will be considered as the direction. So this line has some direction. This length gives the magnitude. So OP, it is a vector having this much of magnitude and having this as the direction. So that becomes a vector. Now how it is represented? It will be represented with the help of this arrow. So OP, if you want to represent, we can put it like this. Simply you write this OP. It means you are considering only the magnitude part of this. If you consider this, so this takes care of the magnitude as well as the direction, because we have put this arrow notation here. We are moving from O to P, O to P. So arrow head should be this side and tail should be this side. So this way we represent any vector. Now it can be considered this point P is the position of this vector with respect to this origin or with respect to this initial point O. So P is the position or the location of the vector with respect to point O. So this is termed as the position vector, means R. It can be represented with this vector R, where R is termed as the position vector, position of point P with respect to O. So we can represent position vector this R, and that is equal to OP. Okay, so that way we represent this. Vectors are also represented in different form as far as the printed books are concerned. It can be represented with a dot. It can also be represented simply by a bar. If you consider this OP bar, so this is also a vector representation. We consider this with the dot. So this is also a vector representation, but mainly these kind of things or these representations are used for the printed book. Sometimes they will make that vector with the bold notation. Let us say vector R, so or OP. So this will be represented in bold. When it is bold letters, it means we consider that it is a vector quantity. So these are the various ways to represent the vector. Just to distinguish, in easy writing, it is not able, we are not able to distinguish whether we are writing a normal letter or a bold letter. Similarly, this dot, it can have some missing, or this bar. So that's why we don't generally represent vector like this as far as our normal writing is concerned. But in printed books, you will find this representation. We generally use this arrow notation to represent the vector. Position vector, this R, point P, position with respect to O, so we can write like this. So these are the various ways to represent the vector. Now, here, now we have different terms. Modulus of the vectors. What is this modulus? Modulus of the vector means the magnitude part. If you have, as we were just discussing, OP. When we write this vector OP, so it carries its magnitude as well as the direction. Now we can separate it. We can separate it means if we want to calculate what is the magnitude of this OP, so that can be represented as OP. You can write like this. Magnitude, mod of a function, it is represented by this vertical bar. So we can put it inside this vertical bar so that this represents the magnitude part of the vector OP. This is one way of representation. So when we say modulus of the vector, it means we are talking only on the magnitude part of that. Instead of writing this, we can also remove this vector notation and we write this OP. So if you write only OP, instead of this vector, this OP, so this also gives the magnitude of this vector OP. Simply OP, there is no need to put this vertical bars here. So remove this vector notation, so that also gives you the, or represent the magnitude of the vector. So it is mod of a vector or the magnitude of the vector. as we have represented the position vector r, so if you want its magnitude, so we can also write like this. Or if you don't want to write vertical, simply you write like this. Remove the vector notation, so this represents the magnitude part of the vector. Now, unit vector, as the name suggests, unit vector, a vector whose magnitude is 1. A vector whose magnitude is 1, that will be termed as the unit vector. So, suppose we have this vector OP. Now, this vector OP can have its magnitude 5 meter. Let us say its direction is east. So, if it represents a displacement of point P with respect to point O, just to have an example, the displacement of point P with respect to O, if it is suppose 5 meter and the direction is east, so it is 5 meter east. So this is a vector quantity having its direction as east, magnitude as 5 meter. So 5 meter east. So this is your direction. This is clear? OP and 5 meter towards east. Okay. There is no need to put that vector notation there. So 5 meter is. Now, if you want to consider a unit vector corresponding to this vector, so unit vector corresponding to this vector OP, that will be equal to how much? 1 meter east. Direction will remain same because it is a vector quantity, but magnitude of that it should be 1. So its unit vector corresponding to this OP, it should be 1 meter east. So unit vector corresponding to this, it is 1 meter east. Now how we achieve this 1 meter? 5 meter is the total magnitude. So 5 meter divided by 5, we got this 1 meter, because just to make the magnitude 1, that quantity has to be divided by the same quantity. It means to achieve this unit vector corresponding to this OP, what should we do? Vector this OP divided by magnitude of OP. Vector OP, because vector OP, so vector OP is how much? 5 meter east divided by magnitude. How much is the magnitude of that OP? 5 meter. So 5 meter is divided by 5 meter, that becomes 1 meter east. So that becomes your 1 meter east. As far as the representation of the unit vector is concerned, it is represented by this cap. Just this cap. So we can consider this OP. So this is the unit vector corresponding to this vector OP. So OP is a vector. Its magnitude is 5 meter. Its direction is towards suppose east. Unit vector corresponding to this vector OP will be that vector divided by its magnitude, so that we get magnitude as 1, and it is represented with the cap. So this unit vector OP, it is vector OP divided by magnitude. So this way we calculate the unit vector corresponding to any vector. Similarly, you have this null vector. Null vector means a vector whose magnitude is there. It is a vector quantity, but its magnitude is 0. So that is considered as the null vector. Proper vector. Proper vector, a vector whose mod is not 0. Any vector whose magnitude is not 0, this normally it is termed as vector, but particularly we can name it as proper vector. Constant vector. Obviously, as the name suggests, the magnitude of the vector will not change. It will always remain fixed. So that will be termed as the constant vector. A vector whose components are constant is called a constant vector. When we say components, component any part of this along x-axis, y-axis, and if it is 3-dimensional case, along z-axis. So if you consider suppose any vector, let us say this is your x-axis, this is y-axis, and this is your vector r. It is inclined at some angle theta. So it will have some value along x-axis, some value along y-axis. So let us say x component it is rm and y component it is ry. So this is the value of this r along this line. This is the value of this r along this line. So this will be termed as the components of the vector. And r is what? The resultant of this and this. Resultant of this and this, so that becomes the resultant of the vector, and here the component of r it is rx as well as this ry. Similarly, so from here we can also have a concept called equality of vector. Equality of vector. When when we say this equality of vector, again as the name suggests, two equal vectors, they will be termed as two equal vectors. So from that we get the concept of equality of vector. Now when we say two equal vectors, so vectors are having two components, magnitude as well as the direction. So two vectors will be equal only when their magnitudes are same as well as directions are same. If any of that is not same, it means they will not be considered as the equal vectors. So magnitude as well as the direction, if both are same, then they will be termed as the equal vector. Let us say we have the vectors A as well as vector B. Now if these two vectors will be termed as equal vectors, or it will represent or it will justify the concept of conditions of equality of the vector, provided magnitude of this vector A is equal to magnitude of vector B. If mod of vector A is equal to mod of vector B, so magnitudes are same, as well as the direction of vector A is same as direction of vector B. If these two conditions are satisfied, then only we will say that vector A, it is equal to vector B. Vector A, it is equal to vector B. In this case, so this is your vector equation. When we say vector A is equal to vector B, it means magnitude of vector A and magnitude of vector B, they are same. Direction of vector A, direction of vector B, it is same. Then only you can write this vector equation, vector A is equal to vector B. So these two conditions have to be satisfied. Then we say that the two vectors are equal vectors, and these are the two conditions to justify the equality of vectors. Geometrically you can represent, suppose this line represents your vector A and this line represents vector B. Length of this line segment, it is same as length of this line segment. When we say length of this and this same, it means the magnitudes are same. Direction, you can see the arrow. It is pointed this side, it is also pointed this side. Yani both are along the same direction. So direction it is same, lengths are same, it means the magnitudes are same. So we will say that this vector A is equal to vector B.